Hi everyone, my name is Zhao King from UC Santa Cruz, a PhD student advised by Maji Sif El Nasser. Today I'm excited to share the column paper about Inspect, an interactive visualization system that helps us understand how players solve problems and make decisions in their games. The title of the paper is Unlocking Player Strategy, a visual journey into players' problem-solving behaviors. Player strategy is significant to game analytics. When we watch how players win or fail, we gain insights into what they find engaging or confusing. For developers, these insights are incredibly valuable for balancing and improving games. And for players, understanding strategy is a chance to learn from experts and discover more effective paths to victory. Most existing analytics tools rely on charts and heat maps. These are great for summaries, but they don't show the actual journey players take. Node edge graphs can show player paths, but once data gets complex, they turn into spaghetti diagrams. And on top of that, analysts spend a huge amount of time pre-processing data before they can even visualize it. Here we introduce the Inspect system that tackles these issues through interactivity. Instead of giving analysts a static visualization, it provides tools to explore player journeys, compare groups, identify patterns, and trace behaviors. It turns complex logs into actionable insights. Moreover, it reduces the need for heavy data cleaning, so analysts can focus on insights rather than wrangling logs. To demonstrate Inspect, we designed a simplified quest game. Players begin with a reveal map quest and choose among 4 follow-up quests. 2 of them are side quests, including ocean exploration and mountain exploration. The other 2 quests lead toward victory, a scientific path, Victory A, and a cultural path, Victory B. Each quest has a round cost, shown in parentheses in this diagram. We simulated 20 players using a Wizard of Oz approach. 7 players are labeled experts, while the other 13 are normal players. 8 players reached Victory A, 7 reached Victory B, and 5 failed to reach any victory. For each player, we recorded their sequence of quests, expertise level, total rounds, and outcome. Here you see the full player journey map. Nodes represent quests. Darker nodes indicate more player visits, and wider edges indicate more common transitions. This gives us an immediate overview of which areas of the game attract most players and which paths dominate. Next, I am going to show several videos illustrating the system. Users can click on any node to see how many players visited it. This is detail on demand. They can also filter the graph, for example, only showing quests visited by more than half of the players. This filtered view reveals the essential structure of the game. Reveal map, build library, found theater, and interestingly, explore ocean emerges as a very popular side quest. Inspect also allows segmentation by metadata, in this case, the player expertise. The difference graph here compares expert players in orange and normal players in blue. Experts tend to choose Victory B more frequently. And when they take Victory A, they prefer the shorter observatory route. Normal players lean toward the longer university route and spend more time on side quests. We can also segment players based on behavior, such as players who succeed versus players who fail. Here, successful players stay focused on the main quest sequences. Failed players, however, often complete only the first step toward victory and then drift away, never committing to a full path, which highlights the difference between successful and unsuccessful players. Combo analysis shows frequent subsequences of actions. We can see which 2-step or 3-step sequences players commonly follow. Reveal map followed by explore ocean is the most common early game combo. And for victory routes, the sequence build library, build university, launch spaceship appears as a dominant path. Backward tracing lets analysts start from a critical event and work backward. Here we trace events leading to Victory A. The system identifies 3 common preceding events: build library, explore ocean, and build university. The distance distribution graph shows how far each preceding event is from the selected event. It provides statistical bar charts and a box plot. For example, Build Library is close to Victory A as expected, but Explore Ocean often appears only a few steps before Victory. The sequence cluster graph groups all paths from a preceding event to the selected event. Each node represents a full sequence, and larger nodes indicate more players followed that sequence. Here, the most common path to Victory A goes through Build University, followed by the 8-round launch spaceship. Finally, the explainability graph helps analysts inspect detailed path elements, like the most common nodes along a route or the top subsequences. Here, 3 options are available: visualizing popular nodes along the route, visualizing the top M most common consecutive n-step subsequences, or visualizing frequently visited but unconnected sequences. For instance, we can visualize 3 most popular nodes from Build Library to Victory A, showing that, in addition to progressing toward Victory, many players also detoured into Explore Ocean. We have 3 case studies to show the analytical value of the system. In Sky Children of the Light, a role-playing game, we compare player behavior across iOS, Nintendo Switch, PlayStation, and PC, and help identify a previously unreported technical issue. Moreover, we use behavioral segmentation to identify potential hackers by selecting a combination of events. In a massively multiplayer online role-playing game, Guild Wars 2, we reveal optimized skill usage sequences associated with higher damage output through combo analysis. In Wake Tales from the Aqualab, an educational puzzle game, we employ the backward tracing feature to trace player behavior leading up to key quest completions and highlight differences in problem-solving approaches. We also conducted a user study, recruited 12 participants to analyze hero ban pick strategies in Dota 2, a multiplayer online battle arena game. The inspect system and the visualization enabled them to ask exploratory questions and derive actionable drafting insights. Compared to traditional data sources like DotaBuff or Liquipedia, participants found Inspect more intuitive, expressive, and useful for interpreting complex draft dynamics. Inspect transforms player journeys into interactive, interpretable visual stories. For competitive games, it can reveal winning strategies and failing pitfalls. For educational games, the system can help identify where students get stuck and adjust their instruction accordingly. If you are a player, the system can help you find better strategies and improve your performance. And if you are a game designer, it can help you improve the game design and provide better experience to players. At last, this work is supported by the National Science Foundation and Benchy.ai. We also want to say thank you to our collaborators, including Johannes Faul, Tina Liu, David Gagnon, and Luke Swanson. Thank you very much for listening.